Welcome to ShowOffer.io, where we're here to help you up-level your interview performance and land your dream offer from top tech companies. My name is Tony, and I'm a technical coach on the ShowOffer platform. At ShowOffer, we specialize in helping candidates navigate the most critical parts of the interview process, from breaking down complex system design problems to prepping for behavioral questions, and even spotting red flags that could result in a rejection or lowball offer. We also offer insightful coaching sessions, live mock interviews, and personalized feedback, all aimed at making you a more confident, structured, and hireable engineer. Today, over the next hour, I'll walk you through one of the most frequently asked system design questions in 2025 for Databricks. That question is, how to design a S3-like distributed file system. To begin, what is Amazon S3? S3 stands for Simple Storage Service. It's one of the most widely used object storage systems in the world. It's designed to store and retrieve any amount of data at any time from anywhere on the web. It's the backbone for backups, media content, machine learning data, logs, you name it. S3 organizes data into something called buckets. Each bucket can store an unlimited number of objects, where each object is typically a file along with its metadata. You don't think in terms of file systems or directories here. It's all flat, but with the illusion of structure through key names. S3 offers some powerful features too. Versioning helps track changes to objects over time. Lifecycle policies allow automatic deletion or archival. And durability? It's designed for 11 nines, meaning your data is safe even if disks or entire servers fail. It's globally distributed, highly available, and optimized for massive throughput. Now, in interviews, when someone asks you to design a distributed file system like S3, they're not asking you to copy AWS. Instead, they want to see if you understand the fundamental principles behind large-scale object storage, things like immutability, eventual consistency, metadata indexing, replication, and durability. Let's dive into the requirements and assumptions ERE guarantees. Then the architecture will be completely different compared to a mission-critical financial system that requires low latency, exactly once delivery with strict security. Let's continue designing our S3-like distributed file system by clearly defining the requirements, constraints, and assumptions. This is critical for guiding architecture decisions and avoiding scope creep during the interview. Functional requirements. We're going to support a simple but powerful API layer. Just 5 key operations. Create directory. This lets users create a new directory. Think of it like making a new folder in a traditional file system. Internally, we'll store this as a metadata entry, possibly with timestamps and parent-child relationships. Delete directory. But with a twist. We can only delete files or empty directories. That simplifies things. No recursive deletion, no dangling references. Create file. This creates a new immutable file. Once it's written, the content can't be changed, which simplifies a lot of consistency issues. But it also means we need to get the right the first time. Read file. This supports partial reads, which are essential when dealing with large files. For example, if you're streaming video or paging through logs, you don't want to load the entire file at once. List directory. This lists the children, files, and subdirectories under a given path. It must be fast, even if the directory holds millions of items. These 5 operations are deliberately narrow to keep the problem tractable, but they still cover the fundamental building blocks of a usable file system. Constraints and assumptions. Now let's talk about the assumptions and constraints that simplify the design but also define its boundaries. 1. Immutable files. This means once a file is written, it can't be changed. There are no edits, no appends, only reads or deletes. Why does that matter? Because immutability eliminates many of the hardest problems in distributed systems. No concurrent writes, no locking on data blocks, And consistency becomes simpler because you're only verifying the correctness of a one-time operation. But the trade-off is, we need to make sure every file write is fully durable. No half-written or corrupted files, because we can't go back and fix it. 2. Mutable directories. While files are static, directories are dynamic. Users can add or remove files at any time, so we need to handle concurrent mutations safely. This pushes us towards strong consistency for directory metadata. We might need transactional semantics for directory-level changes, especially to avoid race conditions or partial state. Think of two users trying to create the same file under /photos 2025/. We need to make sure only one wins, and the system doesn't get confused. 3. Use only primitive infrastructure. This is a big constraint. We can't use cloud services like S3, Bigtable, or GFS. Instead, we're working with building blocks like RDBMS, like PostgreSQL, for consistent relational metadata, KV stores like Redis or RocksDB for fast access to indexed metadata, Zookeeper for distributed coordination, leader election, and locks, local file systems like ext4 or XFS for raw data storage on each node. This forces us to reason about reliability, scaling, and consistency ourselves. It's hard, but it's where the learning is. A quick note on Zookeeper. It's a consistent, replicated coordination service that lets us safely manage locks, file path updates, and metadata changes across nodes. Think of it as the nervous system of the file system. It helps multiple workers act in sync. 4th scale. Millions of users, hundreds of petabytes. This system must operate at massive scale. We're talking billions of files, millions of directories, hundreds of petabytes of raw storage. So it's not enough to build a toy system that works on your laptop. We need to design for horizontal scalability, splitting both metadata and file data across multiple machines and data centers to avoid bottlenecks. We'll need sharding strategies, metadata caching, and probably background compaction or cleanup systems just to keep things responsive. 5th single region, single data center. This assumption simplifies things dramatically. Since we're not worrying about cross-region replication or global consistency, we can avoid complex trade-offs around latency and eventual sync. It lets us focus on designing the core system, metadata handling, replication within one data center, and ensuring durability on local disks. Just keep in mind, this is a simplification for now. Multi-region support is often the first extension interviewers ask about. Non-functional requirements. Let's go over the critical non-functional requirements. These shape how our system behaves under real-world conditions, not just in test cases. 1. Scalability. We need to scale linearly, both for data and metadata. This means we must avoid centralized bottlenecks. Metadata can't live in a single SQL table or a single machine. We'll need sharded or hierarchical metadata storage, smart partitioning, and strategies to balance load dynamically. 2nd, consistency. For metadata, we need strong consistency. If a directory is updated, all users should see the change immediately. For data blocks, we can settle for eventual consistency as long as replicas catch up quickly and reads are resilient. This hybrid model reflects how most real-world systems work: CP for metadata, AP for data. 3. Durability. No data loss. That's non-negotiable. Files must be written to disk and replicated before the operation is considered complete. Even if a node crashes immediately afterward, we should still be able to recover the file. This might mean writing to multiple disks or storing checksums and verifying block integrity periodically. 4th, latency. Low latency is key, especially for read-heavy operations like list directory and read file. Users expect near-instant responses. This pushes us to use fast storage, intelligent caching, and indexes over metadata to avoid full scans. Apart from these 4 non-functional requirements below the line, we also consider Multi-tenancy. Each customer's files should be logically isolated, even if they share physical infrastructure. Extensibility. While we're not building versioning or ACLs today, the system should be designed so they can be added later without a full rewrite. Common pitfalls. During your interview. Before we wrap, here are a few mistakes to avoid. Don't say "like S3" without explaining how you'd build it from scratch. Don't ignore immutability. You can't just update files whenever you want. Don't confuse files and directories. They have different semantics and life cycles. Don't assume metadata is trivial. At scale, it's often the bottleneck. And finally, don't wave away consistency, especially for directories. Correctness matters. If you are targeting to get a high performance during your system interview round, understand the fundamental workflow and discuss on the trade-offs topics is a must-do. Now let's break down the core entities and the APIs of our S3-like distributed file system. Understanding these is crucial because many candidates get tripped up right here by either missing key abstractions or mixing up responsibilities between files and directories. Core entities. At the heart of the system, we've got 5 core entities. First up is the file. Each file is immutable. It can only be written once and then read or deleted. It's content addressed, meaning it's identified by a hash of its contents. Internally, it's split into fixed-size blocks, typically 64 megabytes each, which are then indexed so we can fetch or reconstruct the file efficiently. Next, the directory. This is where things stay mutable. Directories are hierarchical. They map a full path to their child files or subdirectories. They need to support concurrent mutations safely, so they often live in metadata stores with transactional support. Then we have blocks. These are the storage units. Each block holds a slice of file data, and because we hash and deduplicate them, we can save space when storing identical data, like repeated log segments or common binaries. Paths are the absolute string identifiers. Think /photos/2025/image.jpg. These are how users interact with the system, but underneath, we're mapping these strings to metadata entries in a scalable namespace. Finally, customer represents the top-level tenant. This is your unit of isolation. Each customer gets their own logical namespace, making it easier to support multi-tenancy, quotas, and future ACLs. APIs. Let's walk through the APIs and see how each one maps directly to these entities. Create directory path inserts a new directory into the namespace. We're not just creating a label, we're updating the internal path hierarchy under a specific customer. That means inserting a directory entity, linking it to its parent, and ensuring the path tree stays valid. Delete directory path removes a directory, but only if it's empty. This is a safety constraint. It prevents accidental data loss and avoids the complexity of recursive deletes. A common pitfall here is forgetting to enforce this constraint, which could break metadata integrity. Create file path data is more involved. It breaks the file into fixed-size blocks, hashes and stores each one, then links the resulting block list to a new file entry in metadata. It also connects that file to its containing directory. One frequent mistake is conflating the file content and metadata. These need to be stored and managed separately for performance and consistency. Read file, path, offset, length. First loads the file's metadata, then fetches the necessary block range based on the offset. Here, having block indexes up front helps us skip irrelevant chunks and support partial reads efficiently, something critical at scale. List directory path gives us a view of all the child files and directories at a given path. It's read-heavy, so it must be fast, even under high load. One common mistake is storing child entries in a flat table without proper indexing. This slows things down as directories grow. Before we dive into high-level design part, I'd like to shout out where many designs go off the rails during interviews. Mixing up files and directories. They serve fundamentally different roles and need different consistency guarantees. treating metadata as an afterthought. At scale, metadata is often your bottleneck. Ignoring immutability. Once a file is created, it must be locked forever. Avoiding these pitfalls early can save you a ton of redesign effort later. With the entities and APIs mapped out, we're ready to explore the high-level design part. That's up next. In this chapter, we break down high-level design into building blocks, data flows, and data schema. The reason is to follow the given components to build as ground. Link each functional requirement with these building blocks as end-to-end data flow, and illustrate the high-level data schema as a whole. Let's take another look at our given building blocks first. API Gateway. The API Gateway is the entry point for all external requests. It exposes high-level file system APIs like put file, get file, create directory, and others. It is stateless and horizontally scalable, simply forwarding validated requests to the backend service layer. This layer may also handle basic normalization, authentication, and retry logic. File service. The file service is the central orchestrator for file system operations. It coordinates with other components to handle file uploads, reads, and metadata changes. For example, on a file upload, it splits the file into chunks, stores them across storage nodes, updates metadata, and commits the full file atomically. It ensures the correctness and consistency of user-visible operations. Metadata store. The metadata store tracks the structure of the file system. What paths exist, which are directories or files, who owns them, and which blocks make up a file. It stores two main types of metadata: directory hierarchy and file-to-block mappings. This store is strongly consistent and supports transactional updates, making it the foundation of the system's correctness. Chunk Manager. The Chunk Manager maintains a fast access mapping from block hash to the list of nodes that store that block. It acts like a distributed address book for locating content address data. It is backed by a key value store and optimized for high-throughput lookups during file reads and uploads. It may also track block usage for garbage collection. Block store. The block store defines the logic for handling immutable blocks of data. Files are broken into fixed-size blocks, e.g., 64 megabytes, each addressed by a SHA-256 hash. These blocks are never changed once written. The block store handles integrity checks and provides APIs to read or write a specific block by hash. Storage nodes. Storage nodes physically store and serve the blocks on local disk. Each node handles basic upload and download operations for the blocks it holds. Nodes are simple by design and scale out horizontally. They report their status to the Chunk Manager and are periodically cleaned up by background workers. Garbage collection workers. Garbage collection, GC. Workers clean up unused data and metadata asynchronously. When a file is deleted or no longer referenced, GC workers remove its associated blocks from storage and update metadata entries accordingly. These workers run in the background and are carefully throttled to avoid disrupting live traffic. Then, let's come to each data flow one by one to map our functional API calls. Here is a high-level design diagram, where each flow is classified by different color arrows. Create directory. When a user attempts to create a new directory, the request first passes through the API gateway and reaches the file service. The file service parses the full path and checks whether the parent directory exists in the namespace. If the parent is valid and the target path is not already taken by an existing file or directory, it proceeds to insert a new directory entry into the metadata database. This entry links the new directory to its parent, updating the hierarchical structure. This flow ensures that only valid paths are created and preserves the integrity of the overall directory tree. Delete directory. To delete a directory, the request is routed through the API gateway to the file service. The service first verifies that the path points to a directory and not a file. It then checks whether the directory is empty, meaning it has no files or subdirectories. This check is critical as the system is designed to prevent accidental data loss by disallowing recursive deletions. If the directory is empty, the service proceeds to delete its entry from the metadata database. This operation helps users clean up unused paths and ensures that the namespace remains tidy and consistent. Create file. When creating a new file, the file service handles multiple responsibilities. First, it validates that the target path is not already occupied and that the parent directory exists. Then, the file content is broken down into fixed-size blocks, typically 64 megabytes each. These blocks are hashed, deduplicated if necessary, and distributed across the underlying storage nodes for durability and scalability. Once all blocks are successfully stored, the file service creates a metadata entry in the database, linking the file's path to its block list and capturing additional metadata like size and timestamps. This flow respects file immutability and enables reliable, scalable file storage. Read file. To read a file, the file service begins by looking up the file's metadata from the metadata database. It identifies which blocks are associated with the file and calculates which of those blocks correspond to the requested offset and length. This allows for efficient partial reads. The relevant blocks are then fetched from the appropriate storage nodes, assembled in order, and streamed back to the client. Since files are immutable, there's no concern about concurrent modifications, which makes reads highly predictable and fast. This approach aligns well with performance needs, especially when handling large datasets or media files. List directory. For listing the contents of a directory, the file service first confirms that the given path corresponds to a valid directory. Once validated, it queries the metadata database to retrieve all immediate children, both files and subdirectories, under that path. This listing is usually paginated to support directories that contain thousands or even millions of entries. The result is a flat list of names or paths that users can navigate through. This operation is fundamental for users to browse, organize, and manage their stored data, and it needs to be optimized for both speed and correctness. These data flows form the backbone of the system's behavior, and misunderstanding them, especially mixing up how metadata and data storage are separated or failing to enforce constraints like immutability and directory emptiness, is one of the most common candidate pitfalls during interviews. After understanding the data flows, we will come to a shout-out on the data schema. The namespace entries table captures the logical structure of the system, both directories and files, in a unified tree, enabling efficient traversal and listing. The file metadata table focuses solely on file-specific details, such as size and the ordered list of content-addressed blocks, allowing for precise and efficient reads. Finally, the block locations table decouples physical storage from logical structure by mapping each unique block hash to its replica locations, enabling deduplication, replication, and parallel access. Here is the schema, and we can go through each of the tables one by one. First, namespace entries. This table represents the hierarchical structure of the file system and includes both files and directories in a unified schema. The path column acts as the primary key and stores the fully qualified name, for example, /userdataFile1.txt, which allows quick lookups and ensures uniqueness. Name captures the leaf node, for example, in a trie structure, for display or listing purposes, and parent path supports efficient directory traversal and listing via indexed lookups, e.g., for list directory. The type column distinguishes files from directories, enabling proper validation during creation and deletion operations. Timestamps like created at and updated at are useful for auditing, synchronization, and TTL-based policies. This table forms the logical foundation of the file system's namespace. Second, file metadata. This table stores file-specific metadata that is not applicable to directories. The path column, foreign key to namespace entries, links this metadata to a logical file entry. Size bytes tracks the file's total size, helping validate offsets and calculate throughput. Block count gives a quick count of how many blocks make up the file, which is helpful during reads. Block size documents the system's chunking strategy, for example, fixed 64 megabytes, and block hashes stores an ordered list of SHA-256 hashes corresponding to each block. allowing for precise byte range reads using block index arithmetic. The created at timestamp supports audit logging and optional versioning. Together, this schema enables scalable, immutable file reads and writes with minimal metadata overhead. Third block locations. This table maps each content-addressed block hash to a list of storage nodes that hold its replicas. The block hash, SHA-256 of the block content, is the primary key and ensures deduplication. Identical content results in the same hash and is stored only once. Replica nodes holds an array of node identifiers that currently host this block, which supports high availability and latency-aware routing. Ref count tracks how many files reference this block, critical for efficient garbage collection when files are deleted. Last used at helps with eviction policies or diagnosing cold storage patterns. This table abstracts the physical distribution layer and enables efficient, fault-tolerant retrieval of blocks at scale. Now we have a clear look on the high-level design, with a fundamental understanding with the given building blocks, the data flows, and the data schemas. Let's do a deep dive into one of the most performance-critical challenges in distributed file systems: read latency at scale. When you're working with trillions of immutable files and petabytes of data, reads become the dominant bottleneck. This is especially true when users fetch large files made up of dozens, or even hundreds, of data blocks. These blocks are scattered across the cluster, and if we aren't careful, we end up with high fan-out reads, slow or inconsistent replica responses, and metadata lookups that add expensive delays. A naive design will crumble under this kind of scale. So how do we fix it? The answer lies in a layered approach, a combination of parallelism, replica intelligence, caching, and efficient metadata resolution. Let's walk through what happens when a client issues a read file request. The system has to do a lot. First, resolve the file's metadata into a list of block hashes. Then, figure out which replicas hold each block. After that, it has to fetch the actual blocks, possibly from dozens of nodes, and reassemble them into the requested byte range. That's a lot of moving parts, and each one can add latency. So here's the first layer of defense: parallel block fetch with smart replica selection. Instead of pulling blocks one at a time, the system launches concurrent fetches for all the needed blocks. But more importantly, it doesn't just pick a random replica for each block. It uses smart routing, choosing replicas based on live health checks, historical response times, and even network or rack locality. That way, even if one replica is slow or overloaded, the client still gets the fastest possible read path. This parallelism alone brings down read times drastically, especially for cold or long-range reads. But it's not enough. The second layer is block-level caching. Imagine the file service node has a small in-memory L1 cache for recently accessed blocks. On top of that, we layer in a larger SSD-based L2 cache, maybe using Redis, RocksDB, or even local disk. This is perfect for hot content, things like model checkpoints, frequently accessed logs, or user profile pictures. And here's the beauty: because files are immutable, we never have to worry about cache invalidation. A block cached once stays valid forever. This makes caching dead simple and highly reliable. You can even pre-warm the cache for known workloads. Now, both of these layers rely on one key foundation: ultra-fast block location lookup. Every time we need a block, we need to know where to find its replicas. And for that, we use a distributed key value store. This store maps block hash to a list of replica nodes that hold it. It needs to be fast, fault-tolerant, and horizontally scalable. Think Redis cluster, Foundation DB, or something similar. We want millisecond-level latency for multi-key lookups, even at 1 trillion blocks. And by using SHA-256 hashes, we get uniform distribution. No single shard gets overloaded. Each entry is compact but informative. Here is the screenshot of an example. This screenshot contains block hash, list of replica nodes, and reference count for GC. This lets us route reads efficiently and also supports downstream tasks like garbage collection and usage tracking. Even better, if we co-locate KV shards with file service nodes and batch lookups, we reduce network hops and /tail latency. So to wrap up, reducing read latency at scale is not about any one trick, it's about layered optimization. Parallel block fetches with intelligent replica selection, strategic multi-level caching, and lightning-fast block-to-node mapping. Together, these form a resilient, scalable, and high-performance read path that holds up even under extreme scale. Let's now dive into one of the trickiest yet most important parts of designing a distributed file system, ensuring strong consistency during file and directory operations. In a system with thousands or even millions of users interacting concurrently, strong consistency becomes critical, especially when working with a hierarchical namespace where the structure matters. A file must belong to a valid directory. A directory can't be deleted if it still has files in it. And concurrent changes to the same path must never collide or corrupt the system. So, where do we apply consistency guarantees? We focus on the metadata layer, particularly the operations that touch namespace integrity, creating files, creating directories, and deleting either. Under the hood, these map to two core tables, namespace entries and file metadata. These hold the full path structure, ownership, timestamps, and file-to-block mappings. Why does this matter? Let's say two users try to create a file with the same name in the same directory at the same time. Or imagine one user is trying to delete a directory while another is uploading into it. Without proper consistency controls, this leads to orphaned files, ghost directories, or even total corruption of the namespace. That's unacceptable. So to keep everything clean and correct, we implement 3 key strategies. Strategy 1. Transactional metadata store. First, we wrap all file and directory mutations inside a transaction. This gives us atomicity and isolation. We use a relational database like Postgres to ensure that every operation is all or nothing. So when someone creates a directory, we first check that the parent exists, and then insert the new path, all within a single transaction. If something fails, say the parent doesn't exist, we roll it all back. Transactions also allow us to enforce unique constraints, so two users can't create the same path. This is simple, reliable, and works great as long as the metadata fits within a single database instance. But metadata concurrency can still become a problem when multiple users target the same paths. Strategy 2. Path-level locking. To prevent race conditions, we introduce path-level locking on mutations. Anytime we want to modify a directory, say by creating a file inside it, we must first lock the parent directory path. This ensures that only one operation can touch that part of the tree at a time. Let's say user A is uploading file 1.txt into /ab/, and user B tries to delete /ab/ at the same time. Without locking, we risk one operation succeeding while the other leaves the system in an inconsistent state. Locking solves this. Now there are 2 main approaches we can use. Option 1. Database-level locking. This is the lightweight approach. In Postgres, we can use advisory locks. These are user-defined locks identified by a hash of the path. Here's how it works. In this Postgres lock, it is held for the duration of the transaction. No other operation can mutate that path until it's released. The pros? It's simple. No new infrastructure, easy to adopt. And it even works on paths that don't exist yet. But the downside is scalability. Since all locks are coordinated through a single database, it becomes a central bottleneck under high load. If you ever shard the metadata store, it becomes very hard to manage locks across nodes. You also lose observability. No visibility into which service holds a lock or for how long. Option 2. Distributed locking with Zookeeper. This is our recommended approach. Here, we use Zookeeper to acquire distributed locks for each path. If you want to understand more about Zookeeper, You can check our website to read more in our write-up. Before a file mutation, the file service node tries to acquire a lock on something like /locksAB. If it gets the lock, it proceeds. If not, it waits or retries. What makes this powerful is that Zookeeper locks are ephemeral. If the client crashes, the lock disappears. That means no stale lock holders and no manual cleanup. Zookeeper also provides strong fencing guarantees, cross-node coordination, fairness and timeout control, and excellent visibility into what's happening. This approach scales horizontally, works well across services, and ensures consistency even under high concurrency. Yes, it's slightly more complex to set up, but for a distributed file system, it's well worth it. So to sum it up, we guarantee correctness using transactions at the metadata layer, we prevent concurrency issues using path-level locks, and we scale consistency using Zookeeper-based distributed locking. Together, these ensure that your file system remains reliable, conflict-free, and predictable, even with thousands of concurrent users modifying the namespace. Let's now talk about one of the most important questions in any distributed file system design. How do we ensure there's absolutely no data loss? At first glance, many people think this just means keeping backups or replicating disks. But in practice, durability is about much more than disk failures. It's about defending against every possible point of failure in the system, from network flakiness to process crashes to coordination errors. So to truly make our file system durable, we need to handle 4 major risk zones: during uploads, on storage nodes, within metadata commits, and during crash recovery. First, block storage durability. Let's start at the foundation: block storage. Since our files are immutable, each file is broken into fixed-size blocks, say 64 megabytes, and each block is identified by its content hash. Now, we can store these blocks independently and replicate them across multiple storage nodes. A typical approach is triple replication. Each block is stored on 3 separate nodes, but replication alone isn't enough. The key question is, when do we consider a block durable? Our answer: quorum acknowledgement. We require at least 2 out of 3 replicas to confirm the block was safely written. This protects us against a single node failure while avoiding the latency penalty of waiting on the slowest node. Some systems use erasure coding to reduce storage overhead. But for our use case with petabyte scale and single region deployment, triple replication is the sweet spot. It's fast, simple, and resilient. Second, safe ordering between data and metadata. One of the most dangerous mistakes in a distributed file system is committing metadata too early. Imagine a client uploads a file. We write the metadata into the namespace, but the actual blocks haven't been fully uploaded yet, or worse, they failed halfway. Now we have a file path that exists, but the data behind it is either missing or incomplete. That's a recipe for disaster. So we flip the order: blocks first, metadata last. The system first ensures every block is uploaded and replicated to the required quorum. Only then does it perform a transactional commit of metadata, creating the file entry in the namespace. That way, no user ever sees a file that isn't 100% present and valid. And since we key blocks by their hash, all uploads are idempotent. If a crash or retry occurs, the same block just overwrites itself. No harm done. 3. Use write-ahead log. Even with careful sequencing, failures can still happen during upload. Maybe the client disconnects, or the service crashes mid-operation. To protect against that, we add a critical safety net: a write-ahead log, or WAL. Here's how write-ahead log works. Before any real changes happen, the file service writes a log entry that describes its intent. For example, upload file /a/b.txyz. This log is written to a reliable local or replicated store. Only after the WAL entry is recorded do we start uploading blocks and later commit metadata. If the service crashes in the middle, The WAL lets us replay or roll back the operation deterministically. We know exactly what was being done, and we can either finish it or clean it up. This protects us from uncertainty during failure. Without WAL, we'd be left guessing. Was this file half uploaded? Did the metadata commit or not? With WAL, we always know. And it doesn't stop there. WAL helps with crash recovery, resume incomplete operations, atomicity, coordinate writes across metadata and storage, event ordering, replay actions in the correct sequence, garbage collection support, track what should exist and what's orphaned. It's the quiet hero behind high-reliability systems, always logging, always ready to restore order. Fourth orphan cleanup and GC. Even with WAL, some uploads may still fail completely. Maybe the client bailed before metadata was written. In these cases, we need background garbage collection. The system periodically scans for blocks that aren't referenced in the metadata, i.e., their reference count is 0. These are orphaned blocks, and we delete them after a grace period to reclaim space. This ensures the storage layer doesn't accumulate garbage over time and stays clean, lean, and efficient. 5. Long-term data integrity. Lastly, let's talk about long-term durability. What happens months or years later? Disks degrade, bits rot. Silent corruption happens. To fight this, we use hash-based verification. Every block is stored and identified by its SHA-256 hash. At write time, we verify that the stored data matches the expected hash. Optionally, we revalidate these hashes during reads or periodic background scrubbing. And if a storage node fails or gets marked as unhealthy, the system automatically identifies which blocks have lost a replica and re-replicates them from surviving copies. This restores redundancy and keeps data safe, even when hardware breaks. Putting it all together. To sum it up, ensuring durability is not a single feature. It's an ecosystem of defenses. Each layer protects a different part of the life cycle. Together, they guarantee that once a file is uploaded, fully and successfully, it stays safe, available, and intact, no matter what. Now let's shift gears to a question that comes up in almost every system design interview. How does your system scale? In distributed file systems, scale is not just about handling large storage. It's about handling billions of files, trillions of blocks, and millions of user operations per second without falling apart. The answer, at a high level, sounds familiar. We scale horizontally. We keep services stateless where possible, and we partition stateful components carefully. But what really matters in interviews and in real life is being able to break down scalability bottlenecks by system layer and, when asked, to justify your design with rough, reasonable numbers. Let's walk through the 5 layers in our system and see where things break and how we break past them. 1. Metadata database, the namespace layer. The metadata DB holds all our file paths, directory entries, timestamps, permissions, and block mappings. That means every file or directory in the system shows up here. Now let's estimate. Say we store 10 billion files and 2 billion directories. That's 12 billion rows across namespace entries and file metadata. For performance, we want to cap each shard at around 100 million rows. That gives us a lower bound estimate of about 120 database shards. We can shard by customer ID or use a prefix hash of the path, and ideally, we use consistent hashing to avoid large-scale migrations when we add capacity. But remember, metadata is hot. Reads and writes spike during uploads, deletes, and directory listings. So sharding isn't just about storage, it's about concurrency. And if the interviewer asks how we avoid hotspots, use virtual nodes to spread the load more finely. Use consistent hashing to minimize data movement when expanding. Add a routing layer that knows how to forward operations to the right shard efficiently. This layer is often the first to bottleneck, and the hardest to scale if designed poorly. Second chunk manager, the block-to-replica KV store. Next, the chunk manager, which is basically a giant key-value store that maps block hash to replica nodes. Here's the math. Each file has around 10 blocks times 10 B files, which is 100 billion blocks. Each block mapping takes around 200 bytes, so that gives us approximately 20 terabytes of KV data. Now, if each node can handle 500 gigabytes of hot KV entries, we'll need at least 40 partitions. But that's just storage. What about throughput? Each file read triggers approximately 10 block lookups, 100,000 file reads per second, 1 million KV lookups per second. If a single KV node can handle 50,000 QPS, we need at least 20 active KV nodes to support this. The best way to scale this is using sharding by block hash prefix and running a high QPS KV store like Redis Cluster, FoundationDB, or RocksDB. This layer is often underestimated, but it's critical for routing reads correctly and quickly. 3. Storage nodes, where the data lives. Now let's talk about the workhorses, the storage nodes. Here's a reasonable assumption set. Each file equals 10 blocks at 64 megabytes, which is about 640 megabytes per file. So 10 billion files is about 6.4 exabytes of raw data. With deduplication and realistic expectations, let's say we store about 200 petabytes. Using triple replication, that's 600 petabytes of physical storage. If each storage node holds 100 terabytes of usable space, 600 petabytes divided by 100 terabytes equals approximately 6,000 storage nodes. And for performance, say each node supports 5,000 to 10,000 IOPS. If we have 100K active reads per second, we need around 3,000 nodes just to meet I/O demand. We route reads to the least loaded replica. We distribute blocks by hash, and we monitor for skew. That's when one node gets more data or traffic than others. To avoid skew, we again use virtual nodes, rebalancing, and access pattern monitoring. In short, scaling the storage layer is about balancing space, throughput, and replica health at massive scale. Fourth API layer, the front door. The API layer is stateless, and that's a good thing. It means we can scale it horizontally with no coordination. As QPS rises, we just add more replicas. But one tip here, don't let this become a choke point. Use load balancers, distribute requests regionally, and cache hot metadata paths if needed. 5. Background jobs, garbage collection and maintenance. Finally, as the system grows, background jobs like GC and orphan cleanup can start to lag. They scan billions of entries, and if not distributed properly, can create spikes in I/O or metadata contention. To scale this layer, partition GC tasks across metadata shards. Run dedicated GC workers on a schedule. Use backpressure and quotas to avoid fighting with user traffic. If an interviewer asks for rough resource estimates, stay calm and reason step by step. Ask, how many files are we storing? Then, how big is each file? Next, what's the replication strategy? And finally, what are the operational limits per node? These 4 questions let you estimate how many metadata shards, how much KV capacity, how many storage nodes, and how to keep tail latencies low. The goal isn't to be exact. It's to show you understand the scaling factors, the limits, and the realistic levers to scale a petabyte-scale system in production. And that's how we make a distributed file system not just work, but work at scale. That wraps up our deep dive into designing an S3-like distributed file system. From functional APIs to durability, strong consistency, low latency reads, and scaling to billions of files. If you're preparing for interviews at top companies like Databricks, OpenAI, Meta, or Stripe, you already know. These kinds of system design problems are becoming the new baseline. But the truth is, it's not just about knowing the answers. It's about communicating your thought process clearly, breaking down trade-offs, and adapting your design under pressure. That's exactly what we help you train for at ShowOffer. Our coaches are senior engineers and hiring managers from the companies you're targeting. We offer one-on-one mock interviews, detailed feedback, and personalized coaching to help you perform like a top 1% candidate. Whether it's a distributed systems round, a real-world coding challenge, or a behavioral deep dive. So if you're serious about landing your next big offer, don't just prep alone. Prep with ShowOffer. You can check us out at www.showoffer.io or follow this podcast for more breakdowns just like this. Until next time, design with clarity, communicate with confidence, and go get that offer.